In 2023, a physicist named Alison Kirkpatrick stood in front of a room full of colleagues and said something most scientists spend their entire careers avoiding. She believed there was a real possibility that the standard model of the universe was not just incomplete, that it was wrong. Here is what the standard model asks us to accept. Everything humanity has ever seen, every star, every planet, every galaxy, every atom of everything that has ever existed, accounts for only 5% of the universe. The other 95% is made up of dark matter and dark energy, invisible, undetected, required by the equations to make everything else add up. No one has ever directly detected dark matter, not once. Detectors buried deep underground, shielded from nearly every form of interference, have run for years and found nothing. The most powerful particle collider ever built has found nothing. Experiments designed by generations of brilliant physicists, specifically built to find this thing that is supposed to make up most of the universe, keep returning the same answer: silence. And now the James Webb Space Telescope is finding galaxies that should not exist under the dark matter model. Galaxies that are too large, too structured, too fully formed for the timeline the model predicts. At the same time, astronomers have found galaxies that appear to contain almost no dark matter at all, which should be impossible if dark matter is the invisible skeleton holding the universe together. Something is wrong. The question that is now being asked, quietly, carefully, but with increasing urgency inside the physics community, is whether the problem is a missing substance no one can find, or whether it is something far more unsettling. What if dark matter was never there? What if the framework that 95% of modern cosmology is built on is pointing at something that does not exist? And what would it mean for everything we think we know if it turns out we have been building on the wrong foundation all along? Today, we go through the evidence on both sides and sit with one of the most uncomfortable questions in modern science. This channel grows because of people who take a moment to like and subscribe. If you're one of them, thank you. It means we get to keep doing this. It starts with the moment one astronomer noticed the universe refusing to behave the way physics said it should. Long before galaxies carried names, before stars burned long enough to forge carbon or oxygen or iron, the universe existed as something almost impossible to picture. Not empty, not dark, but compressed into a state so dense and hot that space itself had not yet unfolded. Every direction led nowhere else because there was nowhere else to go. Then expansion began. Around 13.8 billion years ago, the observable universe started stretching outward from that early state, cooling as it expanded. Time and space moved together. Temperature dropped with astonishing speed. In less than a second, the first fundamental particles emerged from the plasma. Quarks combined into protons and neutrons. Matter stabilized just enough for the next stage to begin. Within the first few minutes, those particles fused into the simplest atomic nuclei. Hydrogen formed first. Helium followed. Tiny traces of lithium appeared briefly in the fire. Almost everything else did not yet exist. No planets, no galaxies, no living things watching any of this happen. Just immense clouds of primitive matter spreading across a rapidly growing cosmos. For hundreds of millions of years, the universe remained dark, but gravity was already working. Gravity, the weakest fundamental force at small scales, becomes dominant across enormous distances because it never switches off. Tiny variations in density, regions where slightly more matter existed than surrounding space, slowly began pulling gas inward. Clumps formed. Those clumps collapsed further. Pressure rose. Temperatures climbed. Eventually, the first stars ignited. Light returned to the universe. Inside those early stars, heavier elements began forming through nuclear fusion, the process where atomic nuclei merge under extreme heat and pressure. Stars gathered into rotating systems. Those systems became galaxies. Galaxies drifted into clusters containing hundreds or even thousands of members, all connected through gravity across distances measured in millions of light years. This is the standard picture of cosmic evolution: elegant, structured, surprisingly coherent. Under this framework, everything made from ordinary atoms is classified as baryonic matter. That term simply means matter composed of protons and neutrons. You are baryonic matter. Earth is baryonic matter. Every visible star scattered across the night sky belongs to this category, and baryonic matter obeys all four known fundamental forces. Gravity shapes motion across large scales. Electromagnetism binds atoms and produces light. The strong nuclear force holds atomic nuclei together. The weak nuclear force governs radioactive decay and certain fusion reactions inside stars. Together, these interactions explain an enormous portion of the observable universe with remarkable precision, but only up to a point. As telescopes improved during the 20th century, astronomers began measuring how galaxies actually move. They tracked stars orbiting galactic centers. They calculated mass from visible light. They compared gravity predictions against real velocities. The numbers failed, not slightly, catastrophically. Galaxies were rotating far too quickly. Outer stars, especially those near the edges, should have escaped into intergalactic space long ago if visible matter were the only source of gravity present. By every known calculation, galaxies did not contain enough mass to hold themselves together, yet they remained intact. Something unseen appeared to be adding enormous gravitational pull across the cosmos. Either the universe contained vast quantities of invisible matter, or the laws describing gravity itself were incomplete. And from that single fracture in the equations, modern cosmology split into two very different possibilities. In the late 1960s, long after most observatories had gone quiet for the night, Vera Rubin sat beneath the slow mechanical movement of a telescope at Kitt Peak National Observatory in Arizona. Around her, the desert cooled under darkness. Above her, the Andromeda Galaxy drifted across the sky, 2.5 million light years away, immense and silent. Rubin was not searching for mystery. She was measuring motion. Working with instrument maker Kent Ford at the Carnegie Institution in Washington, she used a highly sensitive spectrograph, a device that separates light into wavelengths, to determine how fast stars were orbiting Andromeda's center. The mathematics behind the process were straightforward. Gravity weakens with distance. That principle had described planetary motion successfully since Newton. You can see the pattern in our own solar system. Mercury moves rapidly around the Sun because it sits deep inside the Sun's gravitational pull. Neptune drifts far more slowly at the outer edge. The farther away an object moves from the central mass, the weaker gravity becomes, and the lower its orbital speed should be. Galaxies were expected to behave the same way, but Andromeda refused. As Rubin mapped stars farther from the galactic center, their velocities did not decline. Outer stars were moving almost as quickly as inner ones. Some appeared to travel even faster than the equations allowed. The rotation curve, a graph showing orbital speed across distance, remained flat instead of dropping downward. That should have been impossible. A star moving that quickly at such distances should escape the galaxy entirely. The visible matter simply could not produce enough gravitational force to hold it in orbit. Under known physics, Andromeda should have been tearing itself apart. Rubin assumed an error. She checked calibration data. She reprocessed measurements. She observed again on different nights under different atmospheric conditions. The numbers stayed the same, so she widened the study beyond Andromeda and examined other spiral galaxies across the nearby universe. The pattern repeated everywhere: large galaxies, small galaxies, bright spirals, dim spirals. Every system displayed the same flattened rotation curve. The discrepancy was not isolated. It appeared woven into the structure of galaxies themselves. In 1970, Rubin and Ford published their findings. The reaction inside much of the physics community was restrained at best and dismissive at worst. Rubin faced skepticism not only because the results were disruptive, but because astronomy remained heavily male-dominated. Some colleagues quietly assumed the observations must contain hidden mistakes, but the data kept accumulating. By 1978, Rubin had measured more than 60 galaxies. Independent teams began confirming the same rotational behavior with different instruments and methods. The anomaly hardened into evidence. Rubin reached a careful conclusion. Galaxies appeared embedded inside enormous halos of invisible mass extending far beyond their visible stars. Something unseen was generating additional gravity on colossal scales. She never claimed to know what that invisible component was, only that the universe behaved as though it existed. The distinction mattered. Rubin spent decades refining measurements, while others built theories around them. Honors gradually arrived, including the National Medal of Science in 1993, but the Nobel Prize never did. When she died in 2016, at the age of 88, the problem she uncovered remained unresolved. The galaxies were still rotating too fast. By the early 1980s, astronomy had entered an uncomfortable position. The measurements were no longer isolated anomalies scattered between observatories. They formed a pattern stretching across the visible universe. Galaxies behaved as though enormous quantities of hidden mass surrounded them, shaping their motion from beyond the reach of telescopes. So physicists gave the invisible component a name: dark matter, not dark like charcoal or shadow. Dark in the literal observational sense, it appeared to emit no light, reflect no light, and absorb no detectable light. Every telescope humanity had ever built relied on electromagnetic radiation, visible light, radio waves, infrared, X-rays. Dark matter seemed invisible to all of them, but gravity still responded to it. That distinction became central. Whatever dark matter was, it clearly possessed mass because gravity, the curvature of space-time produced by mass and energy, reacted as though something substantial occupied galactic halos. Yet the same substance appeared absent from every electromagnetic observation ever conducted. You could not photograph it, you could only infer it. Physicists began searching for a particle capable of matching those strange requirements. The leading candidate became known as the WIMP, short for Weakly Interacting Massive Particle. The name described its proposed behavior directly. Massive meant it carried mass. Weakly interacting meant it interacted through gravity and the weak nuclear force, the force responsible for certain radioactive decays, while ignoring electromagnetism almost entirely. A particle like that would drift invisibly through ordinary matter with barely any collisions. The idea gained momentum because it emerged naturally from supersymmetry, often shortened to SUSE, a theoretical extension of particle physics, proposing that every known particle possesses a heavier partner particle. Electrons would have selectrons, quarks would have squarks, familiar matter would be mirrored by a hidden family of heavier companions. Some of those predicted particles had exactly the properties dark matter seemed to require. At the same time, computer simulations were becoming dramatically more powerful. In the 1990s, Cosmologists began constructing virtual universes inside supercomputers, allowing gravity to evolve matter over billions of simulated years. When they filled those simulations with cold, dark matter, meaning slow moving particles traveling far below light speed, something remarkable happened. The large scale structure of the universe emerged naturally. Filaments stretched across cosmic distances like glowing threads. Galaxy clusters formed where those filaments intersected. Vast empty voids opened between them. The resulting architecture resembled astronomical surveys with unsettling precision. The model acquired a formal name, lambda cold dark matter, usually shortened to lambda CDM. Lambda referred to dark energy, the unknown phenomenon driving cosmic expansion faster over time. CDM referred to cold dark matter itself. Together they produced a startling cosmic inventory. According to lambda CDM, ordinary baryonic matter accounts for only 5% of the universe. Dark matter contributes roughly 27%. Dark energy dominates the rest at approximately 68%. Everything you have ever touched belongs to the smallest category, and on paper the framework worked beautifully. Equations aligned, simulations resembled observation, predictions matched large portions of the known cosmos with extraordinary accuracy. But the central ingredient remained hypothetical. Far beyond the Milky Way, nearly 3.7 billion light-years from Earth, two galaxy clusters once crossed directly through one another at several million kilometers per hour. The event lasted hundreds of millions of years. Entire galaxies passed like drifting islands through an ocean of superheated gas. Astronomers eventually named the system the Bullet Cluster. Galaxy clusters are among the largest gravitationally bound structures in existence. Each contains hundreds or even thousands of galaxies, vast reservoirs of hot plasma, and enough mass to bend light across intergalactic distances. Most of the visible matter inside a cluster is not actually contained in stars. It exists as diffuse gas heated to tens of millions of degrees, glowing brightly in X-ray wavelengths. When two clusters collide, that gas behaves like fluid. The galaxies themselves are mostly empty space and pass one another with relatively few direct collisions. But the gas clouds interact electromagnetically. They slow down, compress, heat further. You can picture two weather fronts crashing together across cosmic scales, dragging against each other as momentum bleeds away. In 2006, astronomers combined X-ray observations from the Chandra Space Telescope with measurements from the Hubble Space Telescope and the Magellan telescopes in Chile. What emerged was deeply strange. The visible gas had separated from the gravitational center of the system. To map the gravity, researchers used gravitational lensing, a phenomenon predicted by Einstein's general relativity, in which mass bends spacetime strongly enough to deflect passing light. Light from distant galaxies behind the Bullet Cluster arrived distorted and stretched, allowing astronomers to reconstruct where most of the mass was actually concentrated. The result did not align with the gas. Instead, the strongest gravitational regions appeared ahead of the collision, moving with the galaxies that had passed through relatively undisturbed. The gas, despite containing most of the visible mass, lagged behind in the middle, like debris left after impact. This mattered enormously. If gravity came only from ordinary visible matter, the lensing signal should have followed the gas. But it did not. The gravitational peaks aligned with something apparently invisible, something that moved through the collision without interacting electromagnetically at all. Exactly how dark matter was expected to behave. For many physicists, the Bullet Cluster became the decisive observation, a direct visual separation between visible matter and gravitational mass. Papers described it as a smoking gun for dark matter. Conferences treated the case as effectively settled. The invisible halos proposed decades earlier suddenly appeared less theoretical and more tangible. But the evidence carried an important subtlety. Gravitational lensing measures curvature in spacetime. It reveals where gravity acts strongly. It does not photograph particles directly. No detector inside the bullet cluster captured a WIMP or identified a dark matter particle crossing through space. The observations still depended on interpreting gravity itself. Critics of dark matter noticed that distinction immediately. Modified gravity theories, though strained by the bullet cluster, were not automatically eliminated. If gravity behaves differently across enormous scales, then lensing maps might still emerge without requiring unseen matter. The disagreement shifted from galactic rotation alone to the deeper question of what gravity actually measures. Still, the bullet cluster remained difficult to escape. Any alternative theory now faced a severe requirement. It needed to explain not only why galaxies rotate too quickly, but why gravity in this collision appeared physically displaced from ordinary matter itself. A mile beneath the Black Hills of South Dakota, the old tunnels of the Homestake Mine descend into darkness cut through ancient rock. The air grows cooler as you move downward. Elevators rattle past abandoned shafts once carved for gold. Deep underground, shielded from much of the noise raining constantly onto Earth's surface, physicists built a machine designed to wait for something almost impossible to see. Not light, not radiation, a collision. By the early 2000s, dark matter had become more than an astronomical inference. Simulations matched observations. Galaxy clusters appeared to support the theory. The next step was obvious. If dark matter consisted of real particles moving through the universe, then some tiny fraction of them should occasionally pass through Earth itself. And through you. The leading candidate remained the WIMP, the weakly interacting massive particle proposed by supersymmetry. Weakly interacting was the crucial phrase. A WIMP could drift through entire planets without striking anything because it barely interacted with ordinary matter at all. Detecting one required removing almost every other particle signal in existence. So researchers went underground. Rock overhead acts like a natural shield against cosmic rays, high-energy particles constantly striking Earth's atmosphere from space. Deep below the surface, the background interference drops dramatically. Inside those quiet conditions, detectors could listen for an extraordinarily rare event. A dark matter particle colliding with an atomic nucleus and producing a tiny flash of energy. The Large Underground Xenon Experiment, known simply as LUX, began operating in 2013 inside the Homestake Mine. The detector contained roughly 370 kilograms of liquid xenon cooled to extremely low temperatures. Xenon was chosen because its dense atomic nuclei increased the chance of interaction. Surrounding the instrument sat a massive tank filled with ultra-pure water to absorb stray radiation from the environment. Everything was built for silence. Even trace contamination from surrounding materials could imitate a false signal. Researchers screened construction components individually. Electronics were isolated carefully. Every photon counted. The detector operated until 2016. It found nothing. Not one confirmed dark matter event emerged from the data. No unmistakable WIMP collision. No hidden particle revealing itself inside the xenon chamber. But instead of ending the search, the null result tightened the constraints. Dark matter, if real, interacted even more weakly than expected. So the detector grew larger. LUX evolved into Lux Zeppelin, often abbreviated LZ, containing approximately 10 tons of liquid xenon and becoming the most sensitive dark matter detector ever constructed. Results published in 2022 and again in 2024 reported the same outcome. No detection. The silence spread globally. XENON 1T, operating beneath 3,600 meters of rock inside Italy's Gran Sasso laboratory, reported no confirmed WIMPs. Panda X4T in China, another ultra-sensitive xenon detector, found nothing. DEAP 3600 in Canada, using liquid argon instead of xenon, also reported no signal. Experiment after experiment produced absence. But absence in particle physics carries weight. Every failed detection narrows the range of possibilities, excluding entire categories of hypothetical particles from the map of viable theories. The detectors were not broken. In many cases, they performed beyond expectations. They simply heard no footsteps in the dark. Near the border between Switzerland and France, buried beneath farmland and quiet towns, a circular machine stretches for 27 kilometers underground. Inside that ring, beams of protons travel through vacuum pipes colder than interstellar space, guided by superconducting magnets, powerful enough to bend matter moving at almost the speed of light. This is the Large Hadron Collider. When the collider began operations at CERN in 2008, expectations inside particle physics were immense. The machine was designed to probe energies never before reached in a laboratory, recreating conditions that existed fractions of a second after the Big Bang. Protons accelerated to approximately 99.9999991% of light speed before colliding head-on thousands of times every second. Those impacts briefly produced temperatures hotter than stellar cores. Physicists hoped the collisions would expose hidden layers of reality buried beneath the standard model, the framework describing known particles and forces. One of the leading possibilities was supersymmetry, often shortened to SUSY, the same theory that naturally produced WIMP dark matter candidates. Supersymmetry solved several theoretical problems elegantly. It balanced equations that otherwise appeared unstable at extreme energies. It offered candidates for dark matter. It suggested that every known particle possessed a heavier partner waiting beyond current detection limits. Electrons would gain selectrons. Gluons would gain gluinos. The particle zoo would suddenly double in size. The Large Hadron Collider was built partly to find them. In 2012, CERN announced one of the most important discoveries in modern physics, the Higgs boson, the particle associated with the Higgs field that gives fundamental particles mass. Decades of theory were confirmed. Celebrations spread across the scientific world. But beneath the excitement, a quieter realization settled in. The Higgs appeared almost exactly where the standard model predicted it should, around 125 giga-electron volts. Supersymmetry generally expected something heavier, or accompanied by additional particles nearby in energy. Those extra particles never appeared. Run after run produced the same outcome. No squarks, no leptons, no neutralinos, one of the favored WIMP candidates, no convincing evidence for supersymmetry at all. Data accumulated into trillions of proton collisions, then quadrillions. Each analysis tightened the allowed parameter space further. Physicists began using an uncomfortable phrase, the nightmare scenario. The nightmare was not that the collider failed. It worked extraordinarily well. The nightmare was that nature appeared simpler than theorists hoped. The Higgs existed, but nothing else new emerged beside it. The standard model survived every assault intact, despite strong reasons to suspect it was incomplete. This created a growing tension around the WIMP idea itself. For years, many researchers considered the WIMP miracle deeply persuasive. The phrase referred to a striking coincidence where particles interacting through the weak nuclear force naturally produced the correct abundance of dark matter in the early universe. The math fit beautifully, almost too beautifully, but beauty is not evidence. By 2024, after more than 15 years of operation, the collider had produced no confirmed sign of the particle, supposedly comprising roughly 27% of the cosmos. Underground detectors remained silent. Particle accelerators remained silent. Two entirely different experimental strategies were arriving at the same absence, and the silence was beginning to feel connected. In 1983, while most cosmologists were building increasingly elaborate dark matter models, an Israeli physicist named Mordechai Milgrom looked at the same galactic data and reached a different conclusion entirely. Perhaps the missing mass was not missing at all. Perhaps the equations themselves were failing. It was a dangerous suggestion. Newton's law of gravity had survived for centuries with extraordinary success. Engineers used it to guide spacecraft across the solar system. Astronomers used it to predict planetary motion with astonishing precision. Challenging it was not a small adjustment to physics. It was an attack on one of its deepest foundations. But Milgrom noticed something peculiar about galaxy rotation curves. The discrepancy only appeared at extremely low accelerations, far weaker than anything normally encountered in laboratories or planetary orbits. Near stars, planets, and dense objects, Newtonian gravity worked perfectly. Only at the diffuse outer edges of galaxies did the equations begin to drift away from observation. Milgrom proposed a theory called modified Newtonian dynamics, abbreviated as MOND. Its central idea was remarkably simple. Below a specific acceleration threshold, approximately 1.2 times 10 to the negative 10 meters per second squared, gravity changes behavior. Instead of weakening strictly according to the inverse square law, where force drops rapidly with distance, the decline becomes gentler. Gravity stretches farther than Newton predicted. The effect sounds tiny. It is tiny. The acceleration scale involved is so small that you would barely notice it across everyday distances. But across tens of thousands of light years, inside galaxies containing hundreds of billions of stars, the difference becomes enormous. Suddenly, the outer stars no longer needed invisible mass to remain in orbit. Under MOND, the flattened rotation curves discovered decades earlier emerged naturally from visible matter alone. Feed the distribution of stars and gas into the equations, and the observed galactic velocities appear with surprising accuracy. No hidden particle halo required, no additional mass inserted afterward to make the numbers fit. For many astronomers, that result was unsettling. The theory did not merely explain a few special cases. It generated predictions. One of the most striking became known as the baryonic Tully-Fisher relation, a mathematical relationship connecting the visible mass of a galaxy to its rotational speed. Galaxies, ranging from tiny dwarfs to giant ellipticals, followed the relation with extraordinary precision across roughly 5 orders of magnitude in mass. MOND predicted this directly. Dark matter models could reproduce the relation too, but usually only after complex simulations and carefully tuned feedback effects involving star formation, supernova explosions, and gas dynamics. MOND produced the pattern almost automatically from the visible matter itself. That simplicity gave the theory strange resilience. But MOND carried serious weaknesses. It offered no new particle. It lacked a deeper mechanism explaining why gravity should change at that exact acceleration scale. Most importantly, it struggled to explain galaxy clusters and observations like the bullet cluster, where gravitational lensing appeared separated from visible matter. The broader physics community remained skeptical. Many researchers viewed MOND as an empirical trick, useful for fitting galactic data but incomplete as a fundamental theory. Yet the predictions kept succeeding often enough to prevent the idea from disappearing. Every accurate rotation curve added another complication to the dark matter narrative. The rebel theory refused to go away. Some galaxies arrive quietly into astronomy. A catalog number, a faint smear of light, another distant structure among billions. But in 2018, one particular galaxy forced cosmologists into an awkward pause. Its name was NGC 1052DF2. Using observations from the Dragonfly telephoto array and follow-up measurements from the Gemini Observatory, astronomers reported something astonishing in the journal Nature. The galaxy appeared to contain almost no dark matter at all. Its stars moved too slowly. Its gravitational mass matched nearly all the visible matter already present. Nothing extra seemed necessary. This created an immediate problem for the standard lambda CDM framework. Under that model, galaxies are supposed to form inside dark matter halos, enormous invisible structures providing the gravitational foundation around which gas collapses and stars ignite. Dark matter is not considered optional in this picture. It is the scaffolding itself. But DF2 looked like a galaxy without scaffolding. The object was unusually diffuse, spread thinly across space, yet physically large, comparable in diameter to the Milky Way. According to conventional theory, a system like that should not remain stable without a substantial dark matter halo binding it together. And then a second galaxy appeared. NGC 1052DF4 displayed similar behavior, again suggesting an absence of dark matter where the theory expected large amounts. The findings unsettled researchers because they attacked an assumption previously treated as universal. But the contradictions did not stop there. Another galaxy called Dragonfly 44 seemed to exist at the opposite extreme. Observations suggested it was composed almost entirely of dark matter, roughly 99.99% by mass. Its visible stars looked sparse and faint, while gravity implied a hidden halo enormously larger than the luminous material inside it. Then came AGC 114905, another galaxy where astronomers detected little or no evidence for dark matter through rotational measurements. Similar anomalies emerged within ultra-diffuse galaxies scattered through the Coma cluster. Some appeared dominated by dark matter. Others appeared nearly empty of it. No consistent pattern emerged. That inconsistency became difficult to ignore. If dark matter is a fundamental particle distributed throughout the cosmos, why would some galaxies possess almost none while others contain overwhelming amounts? Why would the invisible scaffolding vary so dramatically between apparently similar systems? Dark matter researchers proposed explanations quickly. One leading idea involved tidal stripping, a process where gravitational interactions between nearby galaxies tear matter away during close encounters. Under this scenario, a galaxy could lose much of its dark matter halo while retaining visible stars. The explanation was physically plausible in some cases, but critics noticed a growing pattern. The explanations arrived after the observations. Each anomalous galaxy required its own specialized history, its own environmental interaction, its own carefully tuned sequence of events. The theory remained flexible enough to absorb the contradictions, but flexibility can become difficult to distinguish from improvisation. Mond advocates pointed directly at that weakness. If galactic behavior depends primarily on visible matter and modified gravity rather than invisible particles, then some of these contradictions soften naturally. The galaxies stop looking impossible and start looking like variations within a different gravitational framework. Meanwhile, the catalog of anomalies continued expanding. Not enough to collapse the dark matter paradigm, not even close, but enough to create pressure points across the edges of the model, small fractures accumulating inside a theory that once seemed increasingly complete. At the edge of observable time, light arrives thin and ancient. Every photon collected from those depths began its journey before Earth existed, before the Sun formed, before the Milky Way reached its current shape. The farther a telescope looks into space, the farther back it looks into history itself. That was the promise of the James Webb Space Telescope. Launched in late 2021 and beginning scientific operations in 2022, JWST was designed to examine the infant universe with unprecedented sensitivity in infrared wavelengths. Infrared light matters because cosmic expansion stretches ancient visible light into longer wavelengths over billions of years. Webb could see objects older telescopes struggled to detect. Cosmologists thought they knew what would appear. According to the standard lambda CDM timeline, the earliest galaxies should have been small, chaotic, and dim. Dark matter halos needed time to merge and grow before large galaxies could emerge. Structure formation was expected to proceed gradually across hundreds of millions and then billions of years. But the first Webb images disrupted that expectation almost immediately. Instead of faint proto-galaxies slowly assembling, astronomers began finding surprisingly massive systems already shining brightly only 300 to 500 million years after the Big Bang. Some appeared highly organized. Some contained mature stellar populations. Several looked too large and too luminous for their age. The phrase universe breakers began circulating among researchers themselves, not journalists, astronomers. One of the most striking discoveries arrived in 2024 with confirmation of a galaxy designated Jade's GSZ 140. The name reflects its extreme redshift, a measure of how much cosmic expansion has stretched its light. Observations placed the galaxy only around 290 million years after the Big Bang, and yet it was already enormous. Its stars appeared abundant. Its structure appeared unexpectedly developed. Under standard dark matter cosmology, galaxies that massive were not supposed to exist so early. The invisible halos required to seed them should not have grown large enough yet. Another object, informally called Maisie's galaxy, intensified the discomfort. Early analysis suggested star formation rates nearly 100 times faster than many models predicted for that epoch. The early universe looked less like a slow construction zone and more like a crowded city already awake before dawn. Researchers responded cautiously at first. Some questioned distance measurements. Others proposed that unusual brightness from superheated gas or active black holes might create misleading impressions. Additional observations refined the estimates, but the underlying tension persisted. Even when corrections reduced the severity of certain claims, the broader pattern remained difficult to dismiss. The timeline no longer fit neatly. Cosmologist Alison Kirkpatrick from the University of Kansas summarized the unease publicly when she said, I have a sinking feeling that we may have gotten something very fundamental about the universe wrong. That statement mattered because it captured the mood spreading quietly through cosmology. Webb had not disproven dark matter. The observations did not suddenly validate MOND or eliminate lambda CDM, but they exposed a growing mismatch between prediction and reality in the earliest stages of cosmic history. The simulations produced one universe. The telescope revealed another. Something inside the chronology of structure formation, whether involving dark matter, star formation, physics, or gravity itself, appeared incomplete. The universe had begun building large galaxies much earlier than expected, and no one yet agreed on why. Every second, the universe becomes larger. Galaxies drift farther apart as space itself expands between them, carrying clusters outward across distances so immense that ordinary intuition breaks down. Cosmologists describe this expansion using a value called the Hubble constant, the rate at which the universe grows measured in kilometers per second per megaparsec, with a megaparsec equal to roughly 3.26 million light-years. For decades, refining that number became one of astronomy's central goals, because hidden inside it is the age, scale, and future evolution of the cosmos itself. There are two primary methods used to calculate the Hubble constant. Both rely on extremely sophisticated observations. Both are grounded in well-established physics. And both produce answers that disagree in ways becoming increasingly difficult to dismiss. The first method looks backward toward the early universe. Researchers study the cosmic microwave background, often abbreviated CMB, the faint afterglow of radiation released roughly 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely through space. Satellites such as Planck mapped tiny fluctuations in that ancient radiation with extraordinary precision. Using the lambda CDM model, cosmologists extrapolate forward from those fluctuations to calculate the present expansion rate. The result comes out near 67.4 kilometers per second per megaparsec. The second method looks locally instead. Astronomers use objects called standard candles, sources whose intrinsic brightness is known, to measure cosmic distances directly. Cepheid variable stars pulse in brightness at predictable rates. Type Ia supernovae explode with nearly uniform luminosity. By comparing true brightness to observed brightness, researchers build what is called a distance ladder, stretching across nearby galaxies. That method produces a different answer, roughly 73 kilometers per second per megaparsec. At first, many scientists assumed the discrepancy would disappear with better data. Precision in astronomy improves constantly. Instruments sharpen, calibration methods evolve. Statistical uncertainties shrink over time. But the gap refused to close. Instead, it widened. Today, the disagreement has reached approximately 5 sigma significance. In particle physics and cosmology, 5 sigma represents a statistical threshold so strong that the odds of random chance producing the discrepancy fall to roughly 1 in 3.5 million. This is not a small calibration issue hiding in decimal places. Two methods measuring the same universe are arriving at incompatible expansion histories. One suggests a slower growing cosmos rooted in early universe observations. The other suggests a faster expanding nearby universe measured directly from astronomical objects around us. Both cannot simultaneously be correct under the same cosmological framework. That realization has unsettled the field profoundly because dark matter and dark energy are deeply embedded inside both calculations. The interpretation of the cosmic microwave background depends heavily on lambda CDM assumptions. Even local measurements connect back to models describing cosmic evolution over billions of years. If some component of the framework is incomplete, the Hubble tension could be its fingerprint. Not every physicist agrees on the severity of the problem. Some researchers still suspect hidden measurement errors, unknown biases, or overlooked astrophysical effects contaminating one side of the calculation. Others believe the discrepancy signals entirely new physics waiting beneath the surface. But year after year, the observations continue improving, and the two universes they describe continue refusing to match. For all its success describing galactic rotation, MOND carried a serious flaw from the beginning. It worked as a modification of Newtonian gravity, but the universe is not ultimately governed by Newton's equations. Modern cosmology rests on Einstein's general relativity, the theory describing gravity as the curvature of spacetime itself. And MOND did not naturally fit inside it. That limitation mattered because relativity governs phenomena Newtonian physics cannot fully explain: black holes, gravitational lensing, expanding spacetime, and the behavior of light near massive objects. A theory challenging dark matter needed to survive not only inside galaxies, but across the entire relativistic universe. For years, MOND lacked that deeper framework. Then, in 2004, physicist Jacob Bekenstein introduced a new approach called tensor vector scalar gravity, abbreviated as TeVeS. Bekenstein was already widely respected in theoretical physics. Decades earlier, he proposed that black holes possess entropy, a measure of disorder or information content, an idea that profoundly reshaped black hole thermodynamics. When Bekenstein turned his attention toward MOND, people paid attention. TeVeS attempted something ambitious. It extended MOND into a relativistic theory compatible with Einsteinian spacetime by introducing additional fields into gravity itself. In physics, a field describes a quantity spread through space and time. General relativity already uses a tensor field to describe spacetime curvature. TeVeS added both vector and scalar fields alongside it, hence the name. The mathematics became considerably more complex, but the framework achieved several important successes. TeVeS reproduced gravitational lensing without requiring invisible particle halos. Light still bent around galaxies and clusters in ways observers measured through telescopes. The theory also retained MOND's accurate predictions for galaxy rotation curves and the baryonic Tully-Fisher relation. For a time, it looked promising, but galaxy clusters remained difficult. Even with modified gravity, the total observed gravitational effects inside some clusters exceeded what visible matter alone could generate. TVs often required adding extra unseen components, sometimes involving massive neutrinos, to close the gap. Then came the bullet cluster observations. The apparent separation between visible gas and gravitational lensing maps placed enormous pressure on TeVeS. Many physicists concluded that some form of unseen matter still seemed necessary. Interest in relativistic MOND theories declined sharply afterward as dark matter retained institutional momentum. But the story did not fully end there. In 2021, physicists Konstantinos Skordas and Tom Zwasnik proposed a new relativistic MOND framework called R-MOND, short for relativistic MOND. Unlike earlier attempts, R-MOND was built specifically to confront the major failures that had haunted modified gravity theories for decades. The bullet cluster, the cosmic microwave background. Those two observations had long been considered the strongest territory of dark matter cosmology. R-MOND aimed directly at them. Early analyses suggested the theory could reproduce both the microwave background structure and gravitational behavior previously thought impossible without dark matter particles. That result surprised many researchers. Not because RMOND suddenly displaced lambda CDM. It did not. The theory remained young, mathematically demanding, and far from universally accepted. But for the first time, a modified gravity framework appeared capable of passing tests once believed fatal to the entire approach. The physics community responded cautiously. There was no rush toward consensus, no widespread declaration that dark matter had failed, but neither could the new relativistic theories be dismissed as easily as before. The boundary between fringe and plausible had shifted slightly, almost quietly, inside modern cosmology. From far above the plane of galaxies, the universe stops looking like scattered objects. It becomes structure, not random, not uniform. A hidden pattern stretches across incomprehensible distance, as though space itself has been woven into something vast and deliberate. This is the cosmic web. It is the largest known structure in existence, spanning billions of light years in every direction. It is composed of filaments, enormous threads of matter, sheets of galactic density, and vast voids where almost nothing resides. Galaxy clusters gather where filaments intersect, forming dense nodes of gravitational concentration. Between them lie regions so empty that light travels through them almost unimpeded. You and I are not outside this structure. We are inside it. Dark matter plays a central role in this picture. Under the standard cosmological model, it acts as the invisible framework that shapes how matter gathers over time. Without it, the web loses much of its coherence in simulations. With it, the structure emerges with striking consistency. To test this, cosmologists built entire universes inside computers. The Millennium Simulation, completed in 2005, was one of the earliest large-scale attempts. Starting from tiny fluctuations in the early universe, it allowed gravity to evolve matter over billions of years. The result was a network of filaments and voids that closely resembled real astronomical surveys. Later projects refined the process. Illustris TNG added more detailed physics, including gas dynamics and star formation. The Eagle simulation incorporated feedback from supernovae and black holes. The Bolshoi simulation focused on dark matter structure with high precision. Each successive model increased resolution and complexity. And each time, the cosmic web reappeared. Filaments formed naturally. Clusters emerged at intersections. Voids expanded in between. The large-scale architecture of the universe looked remarkably stable across different computational approaches, provided dark matter was included as a foundational ingredient. This became one of dark matter's strongest successes. It does not only explain how individual galaxies rotate, it explains why matter in the universe organizes itself into a connected network at all. It gives gravity a hidden scaffold to build upon over billions of years of cosmic evolution. MOND, by comparison, struggles at this scale. Modified gravity theories can reproduce galaxy rotation curves with surprising precision, but generating the full cosmic web from first principles remains difficult. Without an explicit dark matter component, large-scale simulations often fail to reproduce the same filamentary structure in a stable way. For decades, this asymmetry strengthened the case for dark matter. It appeared to succeed where alternative gravity models struggled most. But newer observations are beginning to complicate that confidence. The James Webb Space Telescope is revealing massive galaxies existing far earlier than simulations predict. Structures that should take billions of years to assemble appear only hundreds of millions of years after the Big Bang. The same framework that reproduces the cosmic web seems less accurate when reconstructing the universe's earliest epochs. This creates a subtle tension. A model that matches the large-scale architecture perfectly but misrepresents the timing of its formation is no longer complete. It still describes the shape of the universe with remarkable clarity, but it may be struggling with its history. And in cosmology, timing is everything. When one idea begins to weaken in physics, it rarely disappears. It multiplies. New versions emerge, each more subtle than the last, each designed to preserve what still works while repairing what does not. In the case of dark matter, this process did not narrow the search. It expanded it into an entire catalog of possibilities. By the late 2000s, WIMPs were no longer the only focus. They had become just one entry in a growing list of hypothetical particles. Among the most elusive candidates is the sterile neutrino. A neutrino is already one of nature's strangest known particles, almost massless and able to pass through entire planets without interaction. A sterile neutrino is even more detached. It would interact only through gravity, meaning no electromagnetic force, no weak nuclear interaction, nothing except the faint curvature of spacetime itself. A ghost of a ghost. In 2014, astronomers analyzing galaxy cluster data from the XMM Newton Space Telescope reported a faint excess signal at roughly 3.5 kiloelectron volts. In particle physics, electron volts measure energy at subatomic scales. The signal did not match any known atomic process. Some researchers suggested it could be the decay signature of sterile neutrinos, slowly transforming into detectable photons. The claim generated intense interest. But by 2016, observations from the Hitomi satellite failed to confirm the signal. Shortly afterward, the spacecraft was lost due to a technical malfunction, cutting its mission short. Years later, the X-RISM Observatory launched in 2023 to revisit the same energy range with improved precision. Its results remain under analysis, with no definitive conclusion yet established. Another candidate emerged from an entirely different branch of physics, the axion. Originally proposed in 1977 by physicists Roberto Peccei and Helen Quinn, the axion was not created to solve dark matter. It was introduced to address a symmetry problem in quantum chromodynamics, the theory describing the strong nuclear force inside atomic nuclei. Only later did physicists realize it could also behave as a dark matter particle. Axions are extraordinarily light. Some models suggest they could be billions of times lighter than electrons. Despite their small mass, they could exist in enormous numbers, forming what is sometimes called fuzzy dark matter, a smooth wave-like distribution across galaxies rather than discrete particles. Experiments such as ADMX at the University of Washington attempt to detect axions using strong magnetic fields designed to convert them into faint photons, particles of light. So far, no confirmed detection has been observed. The list continues, expanding. Primordial black holes represent another possibility entirely. These hypothetical objects would have formed in the first seconds after the Big Bang, long before stars or galaxies existed. Unlike stellar black holes, they would not originate from collapsing stars, but from extreme density fluctuations in the early universe itself. Gravitational wave observatories like LIGO have placed strong constraints on how many could exist, but they have not eliminated the idea completely. A small population could still remain undetected depending on their mass distribution. Each candidate introduces new complexity. Each failure narrows one path while opening several more. The result is not convergence toward a single answer, but an expanding landscape of possibilities, a theoretical zoo of particles, fields, and compact objects, all attempting to explain the same invisible gravitational effect. And within that growing collection, one pattern becomes increasingly difficult to ignore. Every time a leading candidate is tested and constrained, the idea of dark matter does not disappear. It adapts, reshapes, and continues. Some ideas in physics arrive quietly, almost cautiously, as if aware of the weight they carry. Others arrive from within the center of established theory itself. Emergent gravity belongs to the second category, proposed not from the margins but from one of the field's most respected theoretical frameworks. In 2016, Dutch physicist Erik Verlinde, known for his work in string theory and black hole thermodynamics, published a paper that reframed gravity in an unexpected way. He suggested that gravity might not be a fundamental force at all. Instead, it could be something that emerges. In Verlinde's picture, gravity arises from the statistical behavior of microscopic information encoded across space-time. Information here does not mean human knowledge, but physical states described in terms of entropy, a measure of disorder or possible configurations. At the deepest level, space-time itself behaves like a system, with thermodynamic properties, slowly organizing and redistributing information. From this perspective, what we call gravity becomes an emergent effect, similar to temperature arising from molecular motion. A large-scale consequence appears immediately. When systems reach extremely low accelerations, precisely the regime where galaxies begin to deviate from Newtonian expectations, emergent gravity predicts an additional effect, not from unseen matter, but from the structure of space-time information itself. This extra contribution produces an acceleration that mimics the presence of dark matter. But no particle is required. One of the most striking outcomes of Verlinde's work is its connection to the Mond acceleration scale. This is the tiny threshold, roughly 1.2 times 10 to the negative 10 meters per second squared, where galaxy rotation curves begin to flatten. Mond had previously introduced this value empirically, derived from observation alone. Verlinde derived a similar scale from theoretical principles, using only thermodynamic arguments and information theory. He reproduced a value closely aligned with what astronomers had measured across galaxies for decades. Two entirely different frameworks, one observational and one theoretical, pointing toward the same numerical boundary. That coincidence drew attention across the field. Emergent gravity also makes predictions that differ from both Mond and dark matter in subtle but testable ways, particularly in galaxy cluster behavior and weak gravitational lensing, a technique that measures small distortions in light caused by mass distribution. Early observational comparisons have produced mixed results. Some analyses show mild agreement, others show clear deviations. Nothing definitive has emerged. The theory itself remains incomplete. It has not yet been developed into a full cosmological model capable of replacing lambda CDM across all scales. It does not yet reproduce every feature of the cosmic microwave background or the full structure of large-scale simulations with consistent precision. But its presence in the scientific conversation carries weight beyond its current status. For the first time, a widely respected physicist working entirely within mainstream theoretical physics reached a conclusion that directly challenges the existence of dark matter itself. Not as speculation from outside the field, but as a possibility emerging from within its mathematical foundations. That shift matters. because it suggests the question is no longer confined to missing particles in space. It may extend into the nature of gravity itself. When cosmologists zoom in on the outskirts of a galaxy like the Milky Way, the expectation is no longer about grand filaments or cosmic expansion. It becomes something smaller, quieter, almost local in scale. Yet even here, the equations of dark matter begin to strain against observation. Simulations built on lambda CDM consistently predict that large galaxies should be surrounded by vast populations of smaller companions. These are dwarf galaxies, faint satellite systems bound by gravity and orbiting their larger hosts like distant echoes of formation. Some models suggest hundreds, others suggest thousands. But when astronomers look outward, the numbers do not match. Across decades of deep sky surveys, including detailed mapping of the Milky Way's halo, only about 50 to 60 dwarf satellite galaxies have been confirmed. The discrepancy is large enough to form what is known as the missing satellites problem. It emerged in the 1990s and has persisted through successive improvements in observation and simulation. The simplest response from dark matter models is subtle invisibility. Many predicted dwarf halos, the small gravitational structures made primarily of dark matter, may exist without ever forming enough stars to become visible. In this interpretation, the satellites are there, just dark, drifting unnoticed through space because they emit no light. But another contradiction emerged soon after. This became known as the too big to fail problem. In simulations, the largest predicted dwarf halos should be massive enough to trigger star formation. They should be bright, stable, and clearly detectable. Yet the expected population of these luminous satellites is not observed in the numbers predicted. Something is still missing. Then a third inconsistency appeared, even closer to galactic structure itself. It is called the core cusp problem. Dark matter simulations predict that density should rise steeply toward the centers of galaxies, forming a sharp spike known as a cusp. Instead, observations of real galaxies consistently show flattened central regions, where density remains relatively uniform across the core. Three separate tensions, all within the same scale of structure. Missing satellites, too big to fail, core cusp. Together they are grouped as small-scale structure problems, a set of inconsistencies that sit inside the otherwise successful dark matter framework. On larger cosmic scales, simulations still perform well. But on the scale of individual galaxies and their satellites, the agreement becomes less stable. Dark matter researchers often respond with baryonic feedback, a term describing the influence of ordinary matter processes such as supernova explosions and stellar winds. In this picture, energetic events inside galaxies push gas outward, reshaping gravitational distributions and smoothing density profiles over time. It is a flexible mechanism. But critics point out that flexibility comes at a cost. The parameters controlling feedback often need careful adjustment to reproduce observed structures. Rather than emerging naturally from first principles, the solutions are tuned after the fact to match what telescopes reveal. MOND and other modified gravity approaches take a different stance entirely. Because they do not rely on large populations of invisible satellites or complex halo substructures, many of these small-scale tensions are reduced or avoided from the beginning. In that sense, the problem shifts again. Not just how galaxies form, but what assumptions are being used to build them in the first place. Some discoveries do not arrive as gradual accumulation. They arrive as a single vibration passing through everything. On a quiet day in August of 2017, Detectors on Earth recorded a ripple in spacetime itself, a phenomenon known as a gravitational wave, which is a distortion in the fabric of space caused by massive accelerating objects. This signal originated from two neutron stars, each only about 20 kilometers wide, yet containing more mass than the Sun, locked in a fatal spiral roughly 130 million light-years away. The event was labeled GW170817. As the stars merged, they released energy in waves that stretched and compressed space while traveling outward at the speed of light. For the first time, humanity was not only observing the universe through light, but also through the direct motion of spacetime itself. The signal passed through Earth and was captured by observatories in Louisiana and Washington. Almost simultaneously, a burst of gamma rays arrived. Gamma rays are the most energetic form of electromagnetic radiation produced in extreme cosmic events such as stellar collisions. These photons traveled across the same intergalactic distance, reaching detectors only 1.7 seconds apart from the gravitational wave signal after a journey spanning 130 million years. That near-perfect synchronization carried enormous meaning. It confirmed that gravitational waves and light travel at virtually identical speeds. The measured difference constrained any deviation to less than 1 part in 10 to the power of 15, an accuracy so extreme that it effectively locks the two speeds together across cosmic history. This result immediately affected theoretical physics. Many modified gravity models proposed before 2017 predicted subtle differences in the propagation speed of gravitational waves compared to light. These differences were not minor details. They were essential to the mathematical structure of those theories. When the measurement arrived, entire classes of models were ruled out within days. Scalar tensor theories, once considered serious alternatives to dark matter within modified gravity frameworks, lost much of their viability. The original formulation of Tevez, which relied on additional fields modifying spacetime behavior, became heavily constrained. The universe had enforced a strict boundary condition on how gravity itself could behave. It was not a philosophical argument, it was a direct measurement. One event eliminated multiple theoretical branches simultaneously, narrowing the landscape of acceptable alternatives in a way no simulation or long-term observation could achieve alone. The precision of the result forced immediate revisions across cosmology and gravitational theory. But the implications did not flow in only one direction. Dark matter itself remained untouched by the constraint. The particle hypothesis, whether WIMPs, axions, or sterile neutrinos, did not depend on gravitational wave speed. It survived the test intact, not strengthened, but also not weakened. Instead, the field shifted. Surviving modified gravity theories, such as Armand and emergent gravity, were carefully adjusted or constructed to remain consistent with the observed equality of light speed and gravitational wave speed. This became a necessary condition for viability, not a theoretical preference. The neutron-star collision did not resolve the dark matter question, but it narrowed the space of possible alternatives with extraordinary efficiency. In a single measured event, the universe removed entire categories of explanation, leaving only those theories that could survive under the strictest relativistic constraints. And in that reduction, the shape of the debate changed again. We now shift scale again, away from clusters and collisions, towards something more intimate in cosmic terms. A single galaxy, our own. But if dark matter exists, it does not sit only in distant structures or rare events. It surrounds every galaxy as an extended, invisible architecture, a vast halo of mass, not shining, not absorbing light, only revealing itself through gravity's influence on motion. Around the Milky Way, this halo is expected to stretch far beyond what any telescope can directly map. Estimates place its reach between 600,000 and 1 million light-years from the galactic center. By comparison, the visible disk of stars spans roughly 100,000 light-years. Everything we see in the night sky occupies only the inner region of a much larger gravitational volume. The galaxy is smaller than its own shadow. Inside that halo, simulations suggest structure does not remain smooth. Instead, dark matter forms clumps within clumps, a hierarchy of density known as substructure. These subhalos are thought to survive galaxy formation, drifting through larger halos like fragments of an unseen ocean current. Some may contain enough mass to influence stellar motion, even without hosting any visible stars, but none have been directly observed. Near Earth, dark matter density is estimated at around 0.3 to 0.4 giga-electron-volts per cubic centimeter. That unit describes energy at particle scale, but translated into everyday intuition, it means that a volume as small as a coffee cup passing through space near you would contain a tiny, continuous presence of dark matter particles. If they exist at all, they would pass through you unnoticed. Not because they are absent, but because they almost never interact. On larger scales, cosmologists predict the existence of dark matter streams. These are coherent flows of dark matter moving through galaxies, shaped by past gravitational interactions. Rather than static halos, they resemble rivers of invisible mass crossing the galactic environment in long, stable trajectories. One such feature, the Sagittarius Stream, is believed to be the remnant of a dwarf galaxy torn apart by the Milky Way billions of years ago. Its stars have been observed. Its dark matter component remains inferred but unconfirmed. Detecting such streams directly would be a major breakthrough. It would reveal not just static halos, but the dynamic motion of dark matter itself within the galaxy. Yet, despite decades of searches, no unambiguous detection of a dark matter stream has been achieved. Still, the consequences of this unseen structure are profound. The Sun orbits the center of the Milky Way at approximately 220 kilometers per second. At that speed, without additional gravitational influence, classical calculations suggest it would not remain in stable orbit. It would gradually drift outward over cosmic time. Dark matter is what keeps that motion stable in current models, not by pulling in a visible way, but by shaping the gravitational landscape through which everything moves, a framework beneath the framework. But that stability is still an inference, not a direct observation. Inside every scientific theory, there is a hidden architecture that is not written in equations. It is made of people, institutions, and shared expectations about what counts as truth. To understand dark matter, we also have to understand this structure. In 1962, philosopher Thomas Kuhn described how science does not evolve smoothly. In his view, it operates through paradigms, shared frameworks that define what questions are worth asking and what answers are acceptable. Over time, anomalies accumulate, small contradictions appear. At first, they are dismissed. Then they become harder to ignore. Eventually, the framework itself begins to strain. Dark matter sits inside one of these paradigms. Since the 1980s, it has become the dominant explanation for galaxy rotation, structure formation, and cosmic evolution. It is embedded not only in theory, but in simulations, telescopes, funding agencies, and entire research programs. It is the baseline assumption behind much of modern cosmology. But that stability has consequences. In practice, scientific institutions tend to reward work that develops existing frameworks rather than replaces them. A young physicist proposing modified gravity does not enter a neutral space. They enter a system already organized around dark matter. That system shapes which papers are published, which conferences are attended, and which proposals are funded. The sociology of science becomes part of the physics itself. Researchers working on Mond and related theories have reported consistent difficulties in gaining institutional visibility. Papers can be delayed or rejected without detailed critique. Conference invitations are limited. Even when results are published, they often remain outside the main narrative of cosmology. Stacy McGaugh, based at Case Western Reserve University, has spent decades analyzing galaxy rotation data. His work shows that Mond predictions align closely with observed galactic behavior across a wide range of systems. These results are published, peer-reviewed, and publicly available. Yet they have not been widely integrated into the standard model of cosmology. They have not been disproven either. This creates a subtle tension in the scientific landscape. A theory can remain unrefuted while still being marginalized if it does not fit the dominant framework. That does not imply conspiracy. It reflects how large scientific communities maintain coherence across thousands of researchers and decades of accumulated work. The inertia is structural, not personal, but history shows that strong structures can still shift. Kuhn's framework suggests that revolutions occur not when a single anomaly appears, but when enough anomalies accumulate to make the existing model less efficient than its alternatives. There are precedents. Newtonian gravity described the universe with extraordinary accuracy for more than 200 years. It was not wrong in most cases. It was incomplete in one specific regime. Einstein did not destroy it. He extended it into a deeper framework that reduced to Newton's laws under familiar conditions. The same pattern may be unfolding here. A system that works across most observations but begins to show tension at its boundaries does not collapse immediately. It persists, adapts, and absorbs corrections. But over time, those corrections begin to accumulate into something larger than adjustment. They begin to resemble transition. At the edge of modern cosmology, everything eventually reduces to a ledger, not of money or objects, but of energy itself, distributed across the entire universe. When we write it down carefully, the result becomes strangely simple and deeply unsettling. Ordinary matter, everything made of atoms and known particles, accounts for only about 5% of the total cosmic energy budget. That includes stars, planets, gas clouds, and every structure we can directly observe. Dark matter is assigned roughly 27%. Dark energy takes the largest share at about 68%. 3 numbers, 1 universe. But none of them behave like anything we directly understand. Dark energy, in particular, is not a substance in the usual sense. It is a name given to the observed acceleration of cosmic expansion, a phenomenon discovered in 1998 when 2 independent research teams studied Type Ia supernova, a class of exploding stars used as standard brightness markers across vast distances. The expectation was simple. Distant supernovae should appear brighter if the universe's expansion was slowing under gravity. Instead, they appeared dimmer. That meant they were farther away than predicted. The only consistent explanation was that the expansion of space itself was accelerating. The discovery was so unexpected that it reshaped cosmology within a few years. Saul Perlmutter, Brian Schmidt, and Adam Riess were awarded the Nobel Prize in Physics in 2011 for confirming the result. Dark energy was introduced to describe this acceleration. In its simplest form, it is modeled as a cosmological constant, a uniform energy density embedded in empty space. The idea itself was not new. Albert Einstein had introduced a similar term in his field equations to maintain a static universe, later discarding it after cosmic expansion was discovered, calling it his greatest mistake. But the modern version behaves differently. It is not a correction for stability. It is an observed effect that drives expansion itself. The deeper problem appears when quantum physics enters the picture. In quantum field theory, empty space is never truly empty. It is filled with fluctuating energy fields. When physicists calculate the expected vacuum energy, they arrive at a value that is larger than what is observed by a factor of 10 to the power of 120. That number is not small. It is incomprehensibly large. This mismatch is known as the cosmological constant problem, and it is widely considered the most severe theoretical disagreement between prediction and observation in all of physics. We are left with a universe where most of its energy content is invisible, unmeasured, or deeply misaligned with theoretical expectations. Dark matter and dark energy are not minor corrections. They define the structure of the model itself. Together, they describe 95% of everything that exists, yet neither has a complete underlying explanation grounded in confirmed particle physics or field theory. At this point, the question shifts subtly. It is no longer only about identifying missing components in the universe. It becomes a question of whether those components represent discoveries of new physics or placeholders for gaps in our current understanding of gravity, matter, and space-time itself. A galaxy is not only a structure of stars, it is also a record. Every orbiting star carries a measurement of the forces that shaped its motion, encoded in velocity, distance, and time. When we study enough galaxies, those individual motions begin to form patterns. In 2016, astronomers Stacy McGaugh, Federico Lelli, and James Schaumbert compiled one of the most detailed comparative studies of galaxy dynamics ever assembled. They examined 153 galaxies, ranging from small dwarfs to large spirals, and measured gravitational acceleration at many points within each system. Acceleration here refers to how quickly stars change their velocity as they orbit, a direct measure of gravitational influence. One version was calculated from visible matter alone. The other was derived from actual observed motion. Then they compared them. What emerged was unexpected in its consistency. Across all galaxies, regardless of size, shape, or environment, the relationship between visible matter and observed acceleration followed a single, tight mathematical curve. Not a broad trend, not a loose correlation, a precise relation. If dark matter behaved as an independent substance, distributed separately from visible matter, the expectation would be scatter. Some galaxies would deviate strongly. Others would cluster differently depending on their individual histories and environments. Random variation would be unavoidable. But that is not what the data showed. Instead, every galaxy aligned along the same curve with remarkable regularity. The pattern became known as the radial acceleration relation. It links the gravitational acceleration predicted from baryonic matter, meaning ordinary atoms, directly to the acceleration that is actually observed in motion. This relation implies something unusual. The effects attributed to dark matter appear to be tightly coupled to the distribution of visible matter itself. In other words, wherever there is more ordinary matter, the additional gravitational effect appears in a predictable way. This creates a tension inside standard dark matter theory. If dark matter is a separate component, then each galaxy should have its own independent distribution of it. Some should be dark matter rich in certain regions and poor in others. The alignment would have to emerge through complex formation histories, feedback processes, and environmental interactions. It requires coordination across billions of light years of structure formation. But in the MOND framework, the relation is not surprising. MOND, or modified Newtonian dynamics, removes dark matter entirely and replaces it with a modification to gravity at low accelerations. In that picture, the tight relation emerges directly from how gravity behaves when accelerations fall below a critical threshold. No extra structure is required. The curve is not an outcome. It is a prediction. Federico Lelli has described the radial acceleration relation as one of the most significant empirical results in modern galaxy dynamics, not because it confirms one theory, but because of how little scatter it shows across such a diverse sample. And as more galaxies are measured with increasing precision, the pattern does not dissolve, it sharpens. For now, the universe continues to present the same message through every galaxy studied. The relationship between what we see and what we infer remains unexpectedly ordered, as if the motion of stars is tracing a rule we have not fully named yet. In theoretical physics, changing a single assumption does not adjust the picture. It replaces the entire frame. If we step into a universe without dark matter, we are not removing a detail. We are rewriting the rules of motion, structure, and time itself. In that scenario, the first shift happens in gravity. Newton's law, describing how objects attract each other through force proportional to mass and distance squared, has been tested with extreme precision within the solar system. It works perfectly for planets, moons, and spacecraft. But in this alternative view, it would begin to fail at extremely low accelerations, far weaker than anything we can reproduce locally. That failure would not appear in laboratories. It would appear only across galaxies. Einstein's general relativity, our most successful theory of spacetime, would remain accurate in strong gravitational fields. Black holes, neutron stars, and planetary orbits would still behave as observed. But in this picture, even general relativity would not be complete. It would represent a limit of a deeper structure, valid only under certain conditions. A weak field correction would be required. A new layer of gravity. This would mean constructing a theory that reduces to general relativity when gravity is strong, yet transforms its behavior when accelerations fall below a critical threshold. That threshold would define where known physics ends and new behavior begins. Several physicists consider this possibility seriously. The history of science provides precedent. Newton described gravity with extraordinary accuracy for over 2 centuries before Einstein showed that it was an approximation embedded within a broader space-time geometry. No one theory remains final forever. In a universe without dark matter, every large-scale simulation would need to be rebuilt. Projects such as the Millennium Simulation and Illustris TNG, which model galaxy formation using dark matter halos, would no longer apply. Their success would need to be reinterpreted under new gravitational rules. The cosmic web would still exist, but its origin story would change. Even the cosmic microwave background, the faint radiation left over from the early universe, would require a new explanation. Its measured peaks and fluctuations currently match dark matter-based predictions with high precision. Without dark matter, Those same features would need to emerge from different physical processes, possibly involving modified gravity or interactions of known particles under extreme early conditions. Some models already attempt this. Certain modified gravity theories, combined with massive neutrinos, real particles known to exist with small but non-zero mass, can reproduce aspects of the observed background structure without invoking dark matter. But these models remain incomplete. The implications extend beyond theory. If dark matter does not exist, then decades of experimental effort, from underground detectors to particle colliders, were searching for a particle that may not be there. It would not mean the work was wasted. It would mean the target itself was misidentified. And in that reinterpretation, the original observation takes on new weight. Vera Rubin did not detect a particle. She measured motion. The flat rotation curves she recorded may not have pointed to hidden matter at all, but to something more fundamental in how gravity behaves at galactic scales. In that sense, the question shifts again. Not what fills the universe invisibly, but whether the rules we use to describe motion are complete at all scales. Deep underground, silence is not empty. It is measured. Every vibration, every stray particle, every flicker of energy is tracked with precision so extreme that even the smallest deviation becomes meaningful. In this controlled stillness, rare signals sometimes appear. In 2020, the XENON-1T experiment, a liquid xenon detector located beneath Italy's Gran Sasso Mountains, recorded one such deviation. The instrument is designed to detect extremely faint interactions between ordinary matter and hypothetical dark matter particles, measuring tiny flashes of light produced when atomic nuclei recoil. During one analysis period, researchers observed a slight excess of electron recoil events, where electrons are unexpectedly knocked loose from atoms without a clear known cause. The energy involved was around 2 to 3 kilo-electron volts, a very low scale in particle physics, yet the frequency stood out from expected background noise. Approximately 3.5 events per ton of detector material per day above predicted levels. The statistical significance reached 3.5 sigma. In particle physics, sigma measures how likely a result is due to chance. 3.5 sigma does not confirm a discovery, but it is strong enough to demand attention. For a brief moment, the field stirred. 3 explanations were quickly considered. One possibility involved solar axions, hypothetical particles produced in the sun that could interact faintly with detectors on Earth. Another suggested neutrinos might possess an unexpected magnetic moment, allowing them to interact more strongly than previously thought. A third, more grounded explanation pointed to trace amounts of tritium contamination, a rare radioactive isotope that could mimic the signal. Among these, tritium was considered the most mundane, but also the most difficult to rule out completely. As analysis improved, background models were refined, additional calibration data reduced the apparent excess, the statistical significance began to weaken. What initially appeared as a possible anomaly gradually blended back into expected noise. Then another experiment responded. Lux Zeppelin, a far more sensitive detector operating with 10 tons of liquid xenon, repeated similar searches. It found no corresponding signal. The excess seen in XENON-1T did not reappear under more precise conditions. The result faded. Not suddenly, but quietly. This pattern is familiar in particle physics. A small excess appears. Excitement builds. Models are tested. Then improved measurements remove the signal. The anomaly dissolves back into statistical variation. It has happened repeatedly over decades of dark matter searches. Each time, the absence of confirmation does something subtle but important. It does not eliminate the concept of dark matter. Instead, it constrains it further. If dark matter exists as a particle, it must interact more weakly than previously thought. Each null result pushes it further into invisibility. The boundaries tighten, and at a certain point, a particle defined only by its lack of interaction begins to approach a conceptual limit, a thing so weakly connected to all known forces that every experiment designed to find it returns silence. Not absence of evidence, but evidence of absence that cannot yet be concluded. At some point, in every long scientific investigation, the instruments stop speaking clearly. The data does not disappear, but its interpretation becomes unstable. In that space, another discipline quietly steps forward, not to replace physics, but to question how physics decides what counts as knowledge. Philosophy of science enters here. Karl Popper, writing in the 20th century, argued that scientific theories must be falsifiable. That means a theory must make predictions that could, in principle, be proven wrong by observation. If no possible experiment can contradict it, then it is not science in the strict sense, but something closer to belief. This idea becomes difficult when applied to modern cosmology. Dark matter, as it currently exists in practice, is not a single fixed hypothesis. It is a framework that adapts. When one form of particle fails to appear in detectors, another is proposed. When simulations do not match small-scale structure, additional mechanisms are introduced. Feedback effects, new particle families, revised interaction strengths. Each adjustment preserves the overall structure of the model. The core idea remains protected. Philosophers of science, such as Imre Lakatos, described this pattern as a degenerating research program. In this structure, a central hypothesis survives not because it is directly confirmed, but because surrounding assumptions expand to accommodate new contradictions. The model does not collapse, it accumulates layers. But accumulation is not the same as convergence. Mond presents a different philosophical profile. Its predictions are narrower and more rigid. It does not easily absorb new parameters. If observations deviate from its core relation, the theory is at risk of failure. That makes it more vulnerable, but also more directly testable. By Popper's criterion, that increased vulnerability increases scientific strength. Still, this does not determine correctness. A theory can be falsifiable and wrong, or flexible and correct. The distinction is about structure, not truth. The deeper question becomes one of timing. In a universe measured across billions of light years, with signals arriving over billions of years, how long should a dominant framework persist without direct confirmation of its central claim? Dark matter has remained the leading model for roughly 4 decades without a confirmed particle detection. During that time, it has explained large-scale cosmic structure with remarkable success, yet its fundamental constituent remains undiscovered. There is historical context for this delay. The Higgs boson was first proposed in 1964. It was not observed until 2012, nearly half a century later. In that case, patience led to confirmation. But there is a crucial difference. The Higgs had no competing framework that explained particle masses and electroweak symmetry breaking with equal consistency. Dark matter does not stand alone in that way. It exists alongside modified gravity theories that reproduce many of the same galactic observations without requiring unseen particles. This parallel structure creates a unique situation in modern physics, where two frameworks can explain overlapping sets of data through fundamentally different assumptions. The question is no longer only about detection. It becomes about how science evaluates competing explanations when both remain mathematically viable, observationally constrained, and yet fundamentally incomplete. Some moments in science do not arrive with a single discovery. They arrive as an accumulation of instruments, each one extending human vision a little further into the same question. Right now, cosmology is entering one of those moments. Across the world, new observatories are preparing to take over the next decade of measurement. Each one is designed to test the same underlying tension from a different angle, as if the universe itself is being examined through overlapping lenses. The Vera C. Rubin Observatory, named after the astronomer who first revealed galaxy rotation anomalies, is preparing for full-sky survey operations. It will image the entire southern sky every 3 nights for 10 years, producing a continuous record of billions of galaxies in motion. Instead of isolated snapshots, it will build a time-resolved map of cosmic structure. That scale changes everything. Patterns that once appeared static will become dynamic. Subtle shifts in galaxy distribution, clustering, and rotation will be tracked across time with unprecedented resolution. Both dark matter models and modified gravity theories will be tested against this continuous dataset. But Rubin is only one piece. The Euclid Space Telescope, launched in 2023, is already mapping the geometry of the universe across distances spanning roughly 10 billion light-years. Its primary goal is to measure how matter and dark energy shape cosmic expansion through weak gravitational lensing, a technique that tracks how light from distant galaxies is slightly distorted by mass along its path. These distortions carry information about invisible structure. At the same time, the Square Kilometre Array, a vast radio telescope system being constructed across South Africa and Australia, will measure hydrogen gas in millions of galaxies. Hydrogen emits a specific radio wavelength that allows astronomers to map galaxy rotation with extreme precision. This will extend the radial acceleration relation to a far larger and more diverse population of galaxies than ever before. Statistical power increases. Patterns become harder to dismiss as coincidence. On the particle physics side, CMBS-4, a next-generation cosmic microwave background experiment, will refine measurements of the early universe's afterglow. It may detect subtle signatures that confirm or exclude several proposed dark matter candidates, tightening constraints on how matter behaved in the first moments after the Big Bang. Meanwhile, underground experiments continue in parallel. Lux Zeppelin, operating deep beneath the Earth's surface, will extend its search for weakly interacting particles. If it continues to observe no detections through its full operational lifespan, the remaining viable parameter space for traditional WIMP dark matter will shrink dramatically. Each experiment targets a different scale. Each probes a different assumption. When combined, their results will define a critical threshold within roughly 10 to 15 years. The overlapping datasets will either converge on evidence for a dark matter particle or eliminate most of the currently favored candidates across a wide range of masses and interaction strengths. At that point, the question will no longer remain focused on technical difficulty or sensitivity limits. It will become a structural question about the model itself, not whether dark matter is difficult to detect, but whether the framework that predicts it is pointing toward something real or toward an assumption that has been carried forward longer than its evidence can currently support. There is a point in every scientific story where explanation stops being descriptive and becomes structural. We are standing at that point now, not at the edge of observation, but at the edge of interpretation itself. If dark matter does not exist, then the universe we observe today still demands an origin for its architecture. The cosmic web, the filaments of galaxies, the vast empty voids between them, all of it still has to emerge from something measurable, something physical, something that existed in the early universe and shaped everything that followed. One possible pathway begins with known particles operating under modified gravity. In this picture, gravity behaves differently at very low accelerations, while ordinary matter remains unchanged. The addition of massive neutrinos, real particles confirmed through experiment, provides another layer of structure. Neutrinos are extremely light, nearly massless in practical terms, yet they are abundant across the universe and move freely through space without being easily stopped or absorbed. They do not carry enough mass on their own to explain galactic structure under standard assumptions. But combined with altered gravitational behavior, they begin to contribute meaningfully to cosmic formation. A second possibility shifts the focus entirely away from particles and toward compact objects. Primordial black holes are hypothetical remnants formed in the first fraction of a second after the Big Bang, long before stars or galaxies existed. If they formed in sufficient numbers, and if their masses were distributed across the right range, they could act as gravitational seeds, pulling matter together into the structures we now observe. No exotic particles required, only extreme early universe conditions. A third approach questions the starting point itself. Instead of asking what invisible component shaped galaxies, it asks whether the initial conditions of the universe have been correctly understood. Small changes in density fluctuations, expansion rates, or early energy distributions could alter how structure forms over billions of years, producing a universe that looks similar to ours without needing an additional matter component. Each of these ideas operates within known or at least physically plausible frameworks. None requires introducing a new fundamental particle that has never been directly detected. None depends on matter that has never interacted with known forces in any measurable way. But none of them is complete. There is no single alternative model that fully replaces dark matter across all scales, from individual galaxies to the cosmic microwave background. Each proposal solves part of the problem while leaving other parts unresolved. That is where the situation becomes unusual. We are left with multiple incomplete explanations that all rely on established physics in different combinations, rather than a single unknown substance. And so the question changes shape again. It is no longer only about what fills the universe invisibly. It becomes about whether our expectation of what should fill it is itself the missing piece. Whether the universe is missing something fundamental, or whether we are. There is a moment in every long scientific dispute when the debate stops looking local. The equations remain, the data remains, but the framing begins to feel too small for the scale of what is being asked. We step into that moment now, where the arguments around dark matter start to resemble something larger than a single unresolved question in physics. Human history shows a repeated pattern. Our models of reality do not fail quietly, they fail by expansion. We once placed Earth at the center of everything, not because of evidence alone, but because of perspective. That idea held for most of recorded history until gradual astronomical measurements began to shift the frame. The Copernican model did not simply move Earth. It redefined what a center even means. Later, in 1918, Harlow Shapley used observations of globular clusters to show that the Sun sits far from the galactic center. The Milky Way itself was not centered on us. That shift was not philosophical at first. It was geometric, but its consequence was psychological. Then, in 1923, Edwin Hubble resolved Cepheid variable stars in Andromeda. These pulsing stars act as distance markers, allowing astronomers to measure cosmic scales. The result was immediate and irreversible. Andromeda was not part of the Milky Way. It was another galaxy entirely. Each of these discoveries did not reduce the universe. They multiplied it. But dark matter presents a different kind of uncertainty. Not a change in location, but a change in substance. If it does not exist, nothing disappears from the universe. Instead, our explanation of structure becomes incomplete in a deeper way. Gravity itself becomes the central question. Among the four fundamental forces, gravity remains the least understood at a fundamental level. We can describe its effects with extreme precision, yet its underlying mechanism resists unification with quantum theory. If dark matter is not a hidden ingredient, then the behavior of galaxies may be pointing toward that missing understanding. The rotation of galaxies, the way stars move faster than expected at their edges, may not be evidence of unseen mass at all. It may instead be a signal that space-time behaves differently across vast, low-acceleration environments, regions so large and diffuse that our local experiments never reach them. That possibility changes the direction of the problem. We are no longer searching for what is missing. We are asking whether the rules themselves shift with scale. But regardless of which interpretation survives, one outcome is already clear. The next generation of physicists will not be entering a finished framework. They will be stepping into a structure that is still forming, still being tested, still capable of fundamental revision. That is rare in science. It is rarer in cosmology. It means the universe is not closing in on explanation. It is still opening outward, revealing that even our most successful models may only be local approximations of something far larger and still not fully seen. There is a quiet fact sitting beneath everything we have learned so far, almost too simple to feel profound at first. You are made of remnants from ancient stars. Carbon, oxygen, iron, all assembled in stellar furnaces across billions of years before becoming part of living matter here on Earth. But the structures that arranged those stars in the first place remain uncertain. The gravitational scaffolding that shaped galaxies, the invisible framework that guided gas into collapsing regions, the unseen influence that determined where light would gather and where it would not, all of this may still be incomplete in our understanding. We describe the motion, we map the distribution, we simulate the outcomes, but the underlying cause is still under investigation. You are, in a very real sense, assembled inside an unresolved equation. That statement is not meant to unsettle. It is simply a reflection of how knowledge has always advanced. Every generation of physics has inherited a universe that felt increasingly precise, yet still contained gaps large enough to reshape everything when examined closely. The absence of final answers is not unusual. It is the normal condition of discovery. The history of science is not a straight path towards certainty. It is a sequence of refinements, where each answer reveals a deeper question underneath it. What once looked complete becomes a special case inside something larger. Vera Rubin demonstrated this in practice. When she measured the rotation of galaxies in the 1970s, she was not searching for a revolution. She was measuring motion. But the data did not match expectation, and that mismatch became persistent rather than isolated. The universe did not respond with explanation. It responded with consistency. Repeated observations showed the same pattern across hundreds of galaxies. The anomaly was not noise, it was structure, and that structure is still present in every data set we refine today. We have built increasingly sensitive detectors buried beneath mountains and deep underground mines, designed to capture signals from particles that may or may not exist. We have launched telescopes that observe galaxies as they were over 13 billion years ago, reconstructing cosmic history from faint ancient light. Each instrument reduces uncertainty, but also expands the area of the unknown. This is not failure, it is scale. Whether the correct explanation eventually involves dark matter particles, modified gravity, or something entirely outside current frameworks, the process itself remains unchanged. We measure, we refine, we revise, and we continue, because the act of asking these questions is not separate from understanding the universe. It is the method by which understanding becomes possible. And in that sense, the most stable feature of cosmology is not the answer we currently hold. It is the willingness to keep the question open, even when every layer of data suggests how incomplete that question still is. Deep beneath mountains and bedrock, the world becomes strangely quiet. It is not the absence of sound in the usual sense. It is engineered silence. Layers of stone absorb cosmic rays that constantly rain through the atmosphere above. Tanks of purified water surround chambers of liquid xenon, filtering out the smallest traces of radiation. Every component is designed to isolate a single possibility from everything else the universe is doing. And still, the instruments listen. They wait for a moment when a particle of dark matter, if it exists in the form we expect, strikes an atomic nucleus. A collision so faint it would produce only a flash of light, a brief electronic trace, a statistical deviation from background noise, a single event among billions of empty readings. But that event does not arrive. Not once in a clean, confirmed way across years of observation, not across multiple continents, multiple generations of detectors, multiple designs pushing sensitivity closer to theoretical limits. The silence repeats itself with increasing precision. That silence is not nothing, it is measurement. It is a boundary being drawn in real time around what the universe is willing to reveal under current assumptions. We cannot say dark matter is absent. Experiments of finite duration cannot prove absence for something defined by non-interaction, but we can say something more precise. We can say that within the energy ranges and interaction strengths we have tested, nothing has appeared. That distinction matters because it forces interpretation. One possibility is that dark matter exists, but is fundamentally different from the weakly interacting massive particles once imagined. It may be lighter, more diffuse, or coupled to forces we have not yet isolated. It may interact so rarely that even the most sensitive detectors remain below threshold. Another possibility is more radical. Dark matter may not be a particle at all. It may be a feature of gravity itself, an emergent property of space-time geometry that becomes visible only at galactic scales. Not something to detect directly, but something to infer indirectly through structure and motion. There is also a more uncomfortable interpretation, that the search has been guided by an assumption that feels natural but may not correspond to physical reality. That what we have called missing matter might instead be a misreading of how gravity behaves when acceleration becomes extremely small. The detectors do not choose between these ideas. They simply record what is not there. And yet the search continues, because every null result sharpens the edges of the question. Every non-detection removes another possible explanation. The parameter space narrows, not toward closure, but toward precision. Above ground, telescopes continue mapping galaxies across billions of light years. In orbit, observatories measure faint distortions in ancient light. In underground chambers, xenon waits in darkness, colder than interstellar space. All of it is synchronized by the same uncertainty. Somewhere in that accumulation of silence, across rotation curves and lensing maps and background radiation fields, the universe is still producing information, not in the form we expected, not yet in a form we fully recognize, but it is there. And the task, quietly and without resolution, is still to learn how to read it. Night settles differently when you think in cosmic scales. Above you, beyond atmosphere and scattered city light, the universe extends in a structure so vast it defies direct intuition. Roughly 100 billion galaxies lie within what we can observe, each one a gravitational system shaped over billions of years. Each galaxy is a slow-moving archive of mass, motion, and time, and each one rotates in a way that refuses full explanation from visible matter alone. Stars move through these systems as if guided by something distributed, something not directly seen, but consistently inferred. Their velocities remain too high at the edges, their stability too uniform across scales where they should diverge. The pattern repeats without exception. Gravity holds everything together, yet its full nature remains incomplete in description. The question at the center of this entire journey, whether dark matter is real or not, does not resolve into a final statement here. It cannot. Not yet. That absence of closure is not a weakness in knowledge. It is a reflection of where knowledge currently stands. The universe does not adjust itself to fit human expectation. It does not simplify when models become elegant. It continues operating under rules we are still learning to interpret. Sometimes those rules appear consistent with invisible matter. Sometimes they appear consistent with modified behavior of gravity itself. The data allows both interpretations to exist in tension. What remains consistent is the act of observation. Across generations, different minds have looked at the same sky and asked different versions of the same question. Vera Rubin measured galactic rotation. Fritz Zwicky noticed missing mass in clusters. Mordechai Milgram proposed a change in gravitational law at low accelerations. Eric Verlinde explored gravity as an emergent property of information. Each approach begins from the same sky and diverges through interpretation. Even the engineers who built underground detectors participate in the same inquiry. They listen for particles that may never arrive, but in doing so, they define the boundaries of what arrival would even mean. We are part of that continuum, not separate from it. Every atom in your body carries a history written in stellar interiors. Every moment of observation extends that history forward. The universe does not observe itself directly, but it does so indirectly through structures capable of reflection. And yet, despite decades of measurement, the central tension remains unresolved. Galaxy rotation curves remain flat. Detectors remain silent. Early galaxies appear too massive too soon. Space-based telescopes continue to reveal structures that challenge prior timelines. Nothing has broken, but nothing has fully settled either. Somewhere within that unresolved space lies the next step, not necessarily an answer, but a refinement of the question itself. It may emerge from data already collected. It may require instruments not yet built. It may arise from a shift in perspective rather than measurement. For now, the universe continues as it always has, expansive and precise, offering only what can be inferred rather than fully seen. And in that quiet gap between certainty and unknown, the work continues,